Whiteboard animation A to Z. Hello and welcome back. This is A level Computer Science 961 in, and today we're going to start with chapter 1, which is information representation, and the subtopic would be 1.1 data representation. Okay, so let's start. This is chapter 1. We're going to start with chapter 1. This is A level Computer Science. The code is 9618, which is obviously updated. The old version was 9608, but now it's 9618. Okay, and today our chapter is chapter 1. The chapter 1 has 3 parts. The first one is data representation. So for now we are starting with this subtopic, which is 1.1. Okay, so the subtopic is data representation. Okay. So let's start with what is binary magnitude. Binary magnitude is obviously any number. Let's say 46 or 57 or 109. Any numbers starting from 0 to 255. This is the range. So taking any number from 0 to 55, what would be the binary representation of that particular number? So in order to find it out, we always, whenever we try to represent in binary from 0 to 255, we're going to represent them in 8-bit form. Okay, so let's make boxes of 8 bits, and let's suppose if I want to get what is the binary representation of 56, and here's how we do things. We just try to do the calculation. Let's say, so this 2 power 0, which is 1, 2 power 1, this 2, 2 power 2, 4, 2 power 3, 8, 16, 32, 64, 128. This is whole 8-bit form. Okay, and now I want to know what is binary representation of this. So let's just say 32 plus 16 plus 8 would be 56. Okay, the others would be 0. And now if I want to add it all up, then 16 plus 8, so it's going to be 56, which means 0 0 1 1 1 0 0 0 is the binary representation of 56. This is a binary representation. Okay, we are saying binary magnitude, which means we are only talking about the magnitude but not signs for now, whether it is positive or negative. If we come to the sign part, then we will say that this leftmost significant bit will be known as the sign bit. Okay, this will tell us whether it is positive or negative, whether the number is positive integer or negative integer. But for now, whenever we talk about binary magnitude, then there's no there would be no concept of sign digit. I mean, whether it is positive or negative. For now, we are focusing on magnitude. It's the same thing like in vector. That vector means magnitude and direction. This is scalar. We are focusing on scalar quantity in physics. Okay, so this is binary magnitude, and now let's talk about prefix. So what exactly are prefix? Prefix are used for whenever we try to install any application on Google Play Store, or whenever we try to download any file or anything, or music or something like that, we always see that there's a prefix, binary prefix, maybe kilo KB bytes, maybe byte, GB bytes. These are all prefix, binary prefix. Okay, and decimal prefix are those prefix like kilobyte, kilo, mega, giga, and tera. These are all decimal prefix. So let's start with binary prefix, and how do we write them out? So binary prefix. Okay, so the name is, like I just mentioned, the name would be kibi, maybe, gibi, Debbie, and baby. Okay, and the symbol, what would be the symbol for each name? The symbol for KB is KIMIGI. TI and PI. This is a symbol, and whenever we try to, okay, you we just mentioned bit, right? 8-bit form. I mean, 8-bit. 1 byte is what 1 byte is equal to 8 bits. Okay, so we can either represent these prefix in byte form or in bit form, but most of the time we try to represent them in kilobyte, kilobits. Okay. If I represent them in bytes, always, we always try to represent these. We can either represent them in bits or byte, but most of the time we try to work with bytes. Okay, so let's write it down. What is, 1 kilo, sorry, KB, 1 KB bytes, the big capital B, it represent bytes. If I write small b, then it would be represented as bits. Okay, so this is 1 KB bytes, and 1 KB byte is equal to 1024 bytes. 1 MB bytes is equal to 1024 KB bytes. Okay, so maybe is greater than KBs and so forth. 1 GB bytes is represented as 1024 MB bytes. 1 TB bytes is equal to 1024 1 GB bytes. 1 PB bytes is equal to 1000 and 1 TB bytes. Okay, so this is the binary prefix, and if we want to write it down as in indices form, then we can write it down like this is 2 of power 10, this is 2 of power 20, this is 2 of power 30, this is 2 of power 40, and this is 2 of power 50. Okay, and this is really important to understand this because it might be helpful in calculations, because most of the time there's always a question about find the file size of this and that. There's always a question whenever you try to do things when you will give the paper in A-level computer science P1. So you will be asked about to calculate the file size of this particular thing and that. So you will use these indices form. Okay, 2 of power 10 is equal to 1 KB byte, 2 of power 20 is equal to 1 BB byte. You can write down like so 2 of power 10 is equal to 1 KB bytes, 2 of power 20 is equal to 1 MB byte, 2 of power 30 is equal to 1 KB byte, 2 of power 40 is equal to 1 TB byte, and 2 of power 50 is equal to 1 PB bytes. Okay, so this is binary prefix, and let's talk about decimal prefix. So the name of the decimal prefix is kilo, mega, giga, and tera, and peta. The symbol we use is K, M, G, T, P. Okay, so 1 kilobyte is equal to 1024 bytes. Not 1024, actually 1000 bytes. 1 MB byte is equal to 1000 kilobytes. 1 GB or 1 gigabyte is equal to 1000 MB bytes, megabytes. 1 terabyte is equal to 1000 gigabytes, and 1 petabytes is equal to 1000 terabytes. Okay, and if I want to write down the indices of this, it's going to be 10 of power 3, 10 of power 6, 10 of power 9, 10 of power 12, and 10 of power 15. Okay, let's suppose if I wanted to know that what is the total byte of 1 megabyte? So 1 megabyte is equal to 1024 kilobytes. So if I break it down, then it's going to be 1024 multiplied by 1024. So this is a whole byte, and then we can just represent this as 2 of power 20. Okay, this is 1 megabyte. 1 megabyte is equal to 1 kilobytes. Okay, 1024 kilobytes. And if you just want to convert this megabyte to just bytes, then we'll just multiply this 1024 multiply 1024, because whenever you try to go from smaller unit, let's say if we're going to centimeter to meter, then it's going to be divided by 100. But if we go from meter to centimeter, then we will do multiplication. Same thing as if we are going from megabyte to kilobytes, then it's going to be just bytes. If we're doing that, then we are going to multiply this. If we're doing maybe to kilo, since this is bigger, so 1 megabyte is equal to 1024 kilobytes. Okay, but if we converting kilobytes to bytes, okay, we need to convert 1 megabyte to bytes. So let's start with 1 kilobytes, 2 bytes. So 1 kilobyte is equal to 1024. So multiplying this by 1024, and if we're going from byte to kilobyte, then we're going to divide this by 1024. So if I'm going from 1 megabyte to bytes, so first of all I'm going to convert this to kilobyte. So it's going to be okay, it's going to be multiplied by 1024. This will become to kilobyte, 1 kilobyte. Sorry, not 1 kilobyte, but just bytes. And then converting byte to megabytes, and it's going to be again multiplied by 1024. Okay, if we're going backwards, then we're going to divide this by 1024, and again we're going backwards, and again divide this by 1024. Okay, so this is how you do the conversion, and it's going to be really helpful when calculating the file size of anything. Definitely it will come in your exam. Okay, so you should be better prepared for this, and let's move on to understanding of the basis of different number systems. Now we're coming to different number system. It's talking about binary, which is the base power, the base is 2. It's talking about denary, the base is 10, and hexadecimal. And the base power is 16. So the base of binary is 2. Okay, which means it has only two numbers, 1 and 0. These are two numbers, possible numbers. In denary, we have the numbers range from 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is denary. Okay, these are the possible numbers. And in hexadecimal, it's starting from A to F. Oh, I'm so sorry. It's starting from 0 to 9. And then after going 10 will be converted to a character, which is A. So it's going to be A to F, which means 10 to A, B, C, D, E, F, 16. Okay, that's why it's known as 16. Or maybe A, B, C, D, E, F. Maybe it's... Actually, it is not 16, it is 15. A, B, C. Okay, it is 15, not 16. This is 15. A to F. Okay, so these are the number systems, and now we need to understand, we need to do the conversions between these three. How do we do the conversion in binary to denary, binary to hexadecimal, and you get the idea. Let's start with binary. Okay, or maybe let me just make a chart, a table. Let's suppose this is binary, this is denary, and this is hexa. If this is 0 0 0 0, we represent denary as 0, hexa as 0. 1 0 0 0, this would be 1, this would be 1, then 0 0 1 0. So what's happening here, you know, these 4 digits, if I write it down like for example this 0 1 0 0, and if I try to know what it would be the number, then 1 2 4 8, so number would be 2. Okay, this is how I'm getting the numbers, representing the numbers in denary. So 0 0 1 1, this would be 2, this would be 3, this again 2 3, then 4 4, then 5 5, okay, 6 6, 7 7, so it would be 8 8, and so forth. This is how it is until it reaches 1 1 1 1, which is 15 in denary, and F as an hexadecimal. We know binary, we know denary. What is hexadecimal and why do we use it? Where do we use it? Hexadecimal is used in assembly languages. Whenever you're going to learn about machine learning, that's where hexadecimal plays a vital role. It is used in developing new softwares or when trying to trace error in programs. Okay, this is what hexadecimal are used for. So whenever you have been asked about what is the advantage or where do we use hexadecimal, you can just write it down like you could just tell them that used in developing new softwares, okay, and tracing errors in programs. That's how you do it. This is binary, this is denary, this is hexa. Now let's focus on the conversions. How do we do the conversions? Okay, binary to denary. Okay, and I've been given the binary 0 0 1 0 0 1 0 1. And I need to convert this in denary. So how am I going to do that? I just told you guys right from the beginning of this video how to convert this, right? You just write down like 1 2 4 8 16 32 64 128. So right here we have 32 plus, okay, and 4 plus 1. We're going to add it up and it's going to be 37. There you go, this is 37. So this is binary to denary. And what happens if we are doing the conversions from denary to binary? So if I'm going from denary to binary, and I've been given the number 37, I need to convert this. Then I'm going to do the division. And how will I do the division? Just divide this number by 2. Okay, 2 ones are 2. Ones are 2. So this game is 17. Then 2 8s are 16, and we get 1 as a remainder. So 2 ones are 2. Then 2 8s are 16. 1 is remainder. Okay. Again, 2 9s are 18. 0 remainder. These are remainders. Then 2 4s are 8. We got 1 as a remainder. Then 2 2s are 4. We got 0. 2 1s are 2. We got again 0. So here we have 1 0 0 1 1. We are starting from here. Okay, start from here. And this is 1 0 0 1 0 1. 4 bits and another 4 bit add extra 0 0. So 4 bit, and this is the answer. And let me see if it is all correct. And yes, this is all correct. The same thing as in here. This is how you do the conversion. Okay, moving on to binary to hexadecimal. How do we do the conversions between binary and hexadecimal? So binary to hexadecimal. Okay, so binary is 1 0 1 1 1 1 1 0 0 0 0 1, and we need to convert this in hexadecimal. Okay, so how do I convert this? I can just split each these. Okay, one. Okay, you need just like 1 byte is equal to 8 bit. We can just call 1 nibble is equal to 4 bit. So these are 1 nibble, 2 nibble, 3 nibbles. Okay. So separate all these nibbles, and then what we're going to do is the same binary way: 1 2 4 8 1 2 4 8 1 2 4 8. So this is 1. Okay, this is 2 plus 4 plus 8, which is going to be 14, and I cannot write 14 in characters. Would be 10 is A B C D E, so it's going to be E. We're going to write down as E, and this is 8 plus 2 plus 1, and this is 11, and if I write it down, then it's going to be B. So the hexadecimal is BE1. This is the answer. Okay, and hexadecimal to binary. Let me see that. Hexadecimal to binary. Okay, so if I say that convert this 45A into binary, then write it down in separate. 4 5 A, and A means 10, and now do it reverse. Write it down like this. Write it down like this: 1 2 4 8. If I put 0, and if I put 1 4, then you will get 1 0 0. There you go. As for this one as well, 1 2 4 8. Okay, this should be 0, this should be 1, this should be 0, this should be 1. So 4 plus 1 would be 5. Same thing here: 1 2 4 8. Okay, we have this should be 1, this should be 0 1 and 0, and all together we have this binary number 0 1 0 1 and 1 0 1 0. This is a binary format for hexadecimal. And now 2 more conversions to go: decimal to hexadecimals. Okay, let's go with another conversions, which is decimal to hexadecimal. Okay, and converting, let's say 68 to hexadecimal. And how do I do that? So the same thing as I did in Denary to binary, like here. When I did Denary to binary, I just divide this by 2, but now I need to do Denary to hexadecimal, so I'm going to divide the number by 16. 16 divided by 68. Let's go. So 16, if I multiply 16 by 4, and one thing you guys need to put in mind, that calculator is not allowed, so you need to do this by hand, these calculations. If you're good in mathematics, then good for you, else you need to do this simple form. 6 4 is 64, 4 ones are 4, and it's going to be 100, and wait 16 4 is 64, 4 ones are 4, so it's going to be, something's not right. 6 4 the 24, actually, sorry, 6 4 the 24, and 4 ones are 4, 64. Okay, so if I put 4, then the remainder would be 4. and that's why we got 44 as a hexadecimal. So this is the answer. This is 44. Okay, it's the conversion between decimal to hexadecimal. And now let's start with hexadecimal to decimal. Hexadecimal to decimal. Okay, converting BE1 to decimal. Okay, so same thing as we did in in binary to in Denary. Hexadecimal to decimal. Okay, here's the thing. Denary or decimal is the same thing, is the same name. You can call it Denary or you can call it decimal. It's the same thing. Okay, no need to get confused. Denary or decimal, it's the same name. Denary, decimal. I just write it down decimal. It should be Denary. Let me just erase this. This is, you can call it Denary, you can call it decimal. It's the same thing. Denary. Here, same thing. Denary. Okay. Hexadecimal to Denary. So similarly, what I did here in binary to Denary, we just did in this way. And what we actually did here is we have done in this way, like 2 of power 0, 2 of power 2, 2 of power 1, 2 of power 2, 2 of power 3, and so forth. So it's going to be 1, 2, 4, 8. That's how I did. Same thing here. What we're going to do is here is 16 of power 0, 16 of power 1, 16 of power 2. Okay, so 16 of power 1, we're going to do like this. 16 of power 0 multiplied by 1 plus 16 of power 1 multiplied by e, and e would be 14. The f is 15, e is 14. Wait, not 14. Could be possible, not 14. 16, it must be 16. E is, okay, sorry, it is 14. E is 14. Then plus 16 of power 2 and multiply by this by b. A is 10, b is 11. Okay, now we're going to do simplification. 16 of power 0 is 1, so this is 1. 16 multiplied by 14, so 16. 14 multiplied 6 4, 6 4, 6 1, 6 12, 18, 24. So 24, 4 1 4, 5 6. 1 6 is 6, 1 1 1, 4, 12, 224. This is 224. And another thing here is, okay, 16 multiplied by 16. How is 16 multiplied by 16? 6 is 36. 6 6 is 36. 6 1 is 6, 7 8 9. 1 6 is 6, 1 1 is 1, 6, and 5 1, 256. So 256 multiplied by 11. How much would it be? 256, 11. Do the multiplication. 6 1 is 6, 1 5 is 5. Then same thing, 1 6, 5 2, 6. It's going to be 11. Carry forward 5 6 7 8 and 2 8 1 6. So it's going to be 2816 plus 224 plus 1. Now do the addition. If I do the addition, 2816, 224 and 1, then it would be 1 1. This is 3, 10 1. This is 3031. Okay, so this is basically the answer. Or wait, might be miscalculating. This is 10 11 1 2 3 4. Actually this is 4, not 3. This is 4, so it's going to be 4. 3041 is the answer. Okay, let me show you how I did this. It's same thing like I did there. It's saying that 2 of power 0 multiplied by 1, 2 of power 1 multiplied by 0, 2 of power 2 multiplied by 0, and so forth. This is how I did, but this is completely direct. You can just do it directly. If you know what, you can just do it directly. Even though you can do it like this as well, you can just check in a computer science book. It would be the same thing. But if you do this in this way directly, then it will save a lot of time. Trust me. It's the best method which I just found it myself, or maybe other teachers know this as well. Okay, so this is the conversions. This is all the conversions. Conversion is completely done. We have done the conversion. We understand about the prefix, what is binary magnitude, and now let's move forward. Okay, the next step would be one's first complement, second complement, second complement, what is overflow, and binary addition, and subtraction. Okay, binary addition and subtraction, and then okay, for now we are focusing on this. So what is first complement and what is second complement? So first and second, these are methods actually. So today we're going to focus on okay. From the beginning, we just talk about the binary magnitude. We didn't discuss about the signs, whether it is positive or negative. No, we didn't. We just didn't. Let's just say we didn't mention about the sign either. We just focused on magnitude. That's it. Okay. But now we're going to see what would be the binary representation if that number is positive, and what is the binary representation if that number is negative. So in order to find out the difference, we use 2's complement and first complement. I'm sorry, this is let's forget about first complement. We always use 2's complement, or when there's a second method as well for representing negative integers. Okay, we are talking about integers, and we need to find out now. How are we going to represent these integers? These either it is positive number. So how am I going to represent a positive number into a binary form? Or if it is a negative number, then how am I going to represent any negative number? Let's say 45, -45, or -67 in binary form, in binary representation. Okay, so let's discuss about integers. So there you go, integers. Okay, it could be positive or it could be negative. Similarly, what we discussed about it, there's a range 0 to 255, so it can be represented in 8-bit form. Same thing here, we're also going to represent integers in 8-bit form, and there's definitely a range. Okay, so let's say obviously we're going to represent these integers in 8-bit form. 7-bit would be the magnitude. This is 7-bit. Okay, 1 2 3 4 5 6 7, and there's the last bit, which we call it the most significant bit. This is known as the sign bit. This is the magnitude, and this is a sign bit. And if the MSB is 0, then we can say it is positive. The number is positive, and if it is 1, then we can say that the number is negative. Okay, and the 7-bit will only represent the magnitude. And so, what is the range? Let's see what is the range. So the max positive number that can be represented. The max positive numbers can be represented from 0 to 127. We can 0 to positive 127. This is the range. And if I call it max negative number, then it can be minus 128 is the max negative number to minus 1. Okay, this is the range. Okay, so this is what we are talking about. So let's suppose if I want to know what is the binary representation of 56, then again I'm going to use the 8-bit. 1 2 3 4 5 6 7 8. We're going to put this 0 because it is positive, and the rest would be the magnitude. So the 1 2 4 8 16 32 64 minus 128. Let's just forget about for now. Let's just I'm writing this anyway. So minus 128, this is 0. Okay, so I want to know what would be the binary representation of positive integer. This is a positive integer. There's a sign. Need to know how to represent this. So it's going to be 1 1 1 and 0 0 0 0. So it's going to be 0 0 1 1 1 0 0 0. Okay, this is the binary representation of a positive integer. And what happens if I say what is the binary representation of a negative 56? How am I going to represent this? Then again, using the same thing, let's make boxes 3 4 5 6 7 8. Okay, so this is 8-bit, and this is 8-bit. And if I try to represent this, in order to represent any negative integer into a binary representation, we use the method 2's complement form. We use a 2's complement form, or we can use another method, the second method. Let's discuss what is 2's complement form first. So first of all, what we do in 2's complement form is we whenever we have been asked about to find the to find the binary representation of any negative integer, in order to use the 2's complement form. So first of all, we're going to find the binary representation of a positive integer, or you can just call it a magnitude. What would be the let's say if I call it what is the binary representation, or what would be in binary format for the number minus 56. So I'm using 2's complement form. Okay, I just decided that. So my step 1 would be what is the binary representation of 56. Okay, so what is the binary representation of only 56? Then if I just do the calculation, I just done it already. So it is 0 0 0 0 1 1 1 0 0 0. This is step 1. Now step 2, convert the step 2 would be convert 0 to 1 and 1 to 0, which means all the digits which are 0 make it 1, and all the ones which all the digits which are 1 would be 0. So this 0 I'm going to make it 1. This 1 0 1 0 0 0 1 1 1. This is the second step. Okay. Step 3. Step 3. Add 1. Just add 1. Okay, when it comes to binary addition or adding any binary numbers, so okay, I didn't tell you guys right now, let me tell you right now. So whenever we try to make an addition of any binary number, let's say 1 plus 0, then it's going to be, this is binary addition. Okay, addition of digits. Okay, so 1 plus 0 would be 1. 1 plus 1 would be 10. 1 plus 1 plus 1 would be 11. And if I go on, 1 plus 1 plus 1 plus 1 would be 100. Again, if I add it up 5 times, then it could be 101, then 1 then 1 then it's going to be 111, then it's going to be 1000, then 101, 1010, 10 okay, yeah, 11, then 1100, and it keeps on going like this every time we add number 1. Okay, so if I add 1 to this, okay, we are going to do the addition. So 1 1 0 0 0 1 1 1 plus 1, and it's going to be 1 plus 1 is 10, so 0 carry forward 1, then again 10 carry forward 1, again 10 carried forward 1, and this is 1 0 0 1 1, and there you go. This is the answer. This is the representation of minus 56. Okay, let me copy paste this. So I just use 2's complement form, and the answer is this. Okay, so if it is positive, then it will look like something like this. If it is negative, it will look something like this. Okay, and now let's talk about the second method. Let's say, okay, let me use this box, copy and paste it in here. Now using the second method, what would be the representation of minus 56? So right here, the most significant bit, if I put 1, then this is minus 128. I put 1 here. Okay, so this is minus 128, and then I put here 1 plus 64, and it would be 64 as well. Yep, 64, and then if I put at 64 54 64, okay, 0, this would be 0, this would be 1. Okay, 1 58 and 1 0 0. If I'm at 8 and 2, then it would be minus 56. There you go. This is the second method, and if I try to compare this, or maybe I've just done something wrong, minus 128 plus 64, and this would be 64. Okay, you don't need to add 2. My mistake. It would be 0. So this is minus 56. So you can use any of the method, but you need to remember this 2's complement form, because this will definitely you were definitely going to be asked about what is a 2's complement form. How do we how do we try to solve this in 2's complement form? This is all part of the exam. This is all part of the paper. You will be asked for it. So you need to remember what is 2's complement form. And when the step 3 is 1's complement. The step 3 is known as 1's complement form. This is 1 complement form. Or wait, actually this is not complement form. The step 2 is 1's complement form. The step 2 is 1's complement form. Okay, this is the 1's complement form. Okay, so this is how you do it. Inverting 0 to 1 or 1 to 0, just invert it, and there you go, you got this. Okay, so there you go, we have understood what is second complement form or second method. What is overflow? Okay, let's start with binary addition and subtraction. You may be asked, let's say you may be given the question about, let's say if you're adding, what would, let's say we given the question that 64 plus 28. So this is binary addition. So what would be the binary representation of 64 and binary representation of 28? You can do this separately, or you can just directly do the addition yourself. Wait, let's just say if I do this. So the binary representation of 64 would be, if I just say, okay, this is 64, right? 1 2 4 8 16 2 64 128, this is 0, this is 1, 0, 0, 0, 0, 0, 0. Okay. So this is the binary representation 64. And what is the binary representation of 28? If I just say 1, 2, 4, 8, 16, 32, 64, 1, 28, 0, 0, 0, 1, and again 1, and again 1. This is the binary representation of 28. Okay. Now if I do the addition, 0, 1, 0, 0, 0, 0, 0, 0, here 0, 0, 0, 1, 1, 1, 0, 0. Doing the addition, 0, 0, 1, 1, 1, 0, 1, 0, and you will get this. If I see it correctly, then this is, what is the value? 2, 4, 8, 16, 32, 64, plus 64, plus 16, plus 8, plus 4, and this is definitely going to be 92. This is the answer. And again, this is obviously 74, 84. Okay, something is wrong. 70, 84, 84 is plus 8, 92. Yes, it is right. So the binary representation of 92 is this. You can either do it directly. It depends on the question. What are they going to ask you about? Okay, and let's say if I do the subtraction. Let's suppose if I do the subtraction. So I'm doing the subtraction like 72 minus 33. Okay, so this is the question. So what is the binary representation of 72? It's going to be, okay, 1, 2, 4, 8, 16, 32, 64, 1, 28. Okay, and it's going to be 1, 0, 0. Okay, another thing here is this is minus 128. Since we are working in, since we are working in, in integers, this is minus 128. This also minus 128 and minus 28. Okay. So where was I? Okay, here it is. So 1, 2, 4, 8, 16, 32, 64, and minus 128. So 0, 1, 0. Okay. If I put 74, no, not this one, and if I put 64 plus 8, then it would be, yup, this is it. This is the binary representation of 672 and minus 33. Minus 33. I need to convert this in binary format. So I'm going to use here 2's complement form. Same thing, obviously, which I just told you guys. First of all, I'm going to see what is the binary representation of 33. So if I just see like 1, 2, 4, 8, 16, 32, 64, 1, 28. Okay, this is going to be, okay, this is minus 128. Okay, so 0. Okay, yeah. So 0, this is 64, 0, this is 1, and 1, 0, 0, 0, 0. So the binary representation is this 4-bit 0, 0, 0, 0. Okay, so this is the binary representation. Now invert 0 to 1 and 1 to 0 using step 2. I'm going to invert this, so this is 1, 1, 0, 1, 1, 1, 1, 0. Now add 1, the step 3, so this is going to be 1, 1, 1, 1, 1, 0, 1, 1, and this is a binary representation of minus 33. Now we are ready to do the subtraction. So 0 1 0 0 1 0 0 0 and 1 1 0 1 1 1 1 0. Bear in mind that we are doing the subtraction, even though I just made it. We are doing the addition of these binary, but even though we just already changed this, right? We have already changed this into binary format, and now we're going to do the addition. Similar, it's the same thing as, we're doing subtraction. I mean, we're just doing this, right? The binary format of this is here, and the binary format of minus 33 is here. Now we're going to do the addition of these binary numbers. So 0 1 1 1 plus 1 is carry forward 0, and 1 is up, then again carried forward 1 1, carried forward 1, and carry forward and 1. So this is the extra bit. We're going to neglect this. Okay, this is extra bit is neglected. Okay, and this is the answer. So if I do it mathematically, so this is okay, 42 41 40 39. This is 39 49 59 69 72. So the binary representation of this is the binary representation of 39. If I confirm it, then 1 2 2 plus 4 4 8 16 32 plus 32. If I do this, then 36 27 30. I've done a mistake here. This clearly written here is 1, and I've just put here 0. Shouldn't be that. This is 1. This is 1, so it's also going to be 1, and so it's going to be 39 since it is 2 4 plus 32, and it should be, but if I written here so it's going to be 1 plus 2 plus 4 16 32 1 2 4 8 16 32 plus 32 1 2 4. Okay, wait a minute. Oh yeah, 1 2 4 8 16 32. So 32, and it's equal to 33 4 5 6 7 8 9 39. So this is the binary representation of this is what I'm talking about. It's a binary representation of 39. This is how you do binary subtraction and binary addition. This whole thing was binary subtraction, and this was binary addition. Okay, so this is done. 2's complement and second method done. What is overflow? Okay, from the beginning I just told you guys, I discussed in the video that there is a range. Where have I discussed it? Okay, here it is, that there is definitely a range. Okay, whenever we try to convert any integer number into a binary representation. So overflow is simply means that going outside the range, which means overflow. Obviously it will give an error, so that's what we call it. So the range is, we need to be careful whenever we try to do the binary addition or subtraction, because it must be in the given range. If we take any numbers, it must be in the given range. If we try to addition two numbers, it must be in the given range. If we try to do the subtraction of two integers, it must be in the given range. If it is outside of the range, then it will be known as overflow. So the range is of both addition or subtraction of binary of any binary integers. When addition or subtraction of binary numbers, the integers must be in this form: minus 128 till plus 127. This is the range. Okay, if for example, if I take let's suppose if I take the addition of 82 plus 69 and if I try to find the binary representation of 82, the binary representation of 82 is 0 1 0 1 0 0 1 0, and the binary representation of 69 is 0 1 0 0 and 0 1 0 1. So this is the binary representation of 82 and this is the binary representation of 69. And if you try to do the addition, if we try to plus to the addition, so 0 1, let me write in different color. So 0 1 0 1 0 0 1 0 1 0 1 0 0 0 1 0. Do the addition, so this is 1, this is 1 1 0 1 0, carry forward and 1. Got this. And if you try to see that what would be the binary representation of this, then accordingly to this it would be okay. Now you see this here, you can clearly see here that this is 1, and what it means that minus 128, so this is representing a negative number. So if let me do it directly, 1 plus 2 plus 4 1632 1630. Okay, so this is minus, okay, wait, minus 128 plus 64 32 16 4 2 1. So this is minus 105. So let me ask you, why, if we try to add to these two numbers, then where did 105 came from? Come on, 82 plus 69 is 151, not minus 105. This is exactly what this binary representation is telling us. It's telling us that the answer is minus 105, which is impossible, which means there is an overflow. And why there is an overflow? Because whenever we try to we are adding 82 plus 69, which is exactly 151, and 151 is outside the range of this. It must be in the range of 127, but it's outside the range, it is 151. So this is known as overflow. This is overflow because obviously it's given an error. It cannot be minus 105. It's giving error. Okay, this is overflow, and yep, there you go. Done. Now what we have what we got left. Okay, now we need to understand about BCD and ASCII and Unicode. And then that's it. The chapter is done. So what is BCD? Okay, BCD is binary coded decimal. What is this? Okay, so what is BCD? BCD uses a 4-bit code to represent each Denary digit. It uses a 4-bit code. To represent each Denary digit. Okay, and the representation of digits, it can be used in okay, it's using a 4-bit code, which means it's using a nibble, and it's used in application such as in that requires Denary. It used in application that requires Denary digits to be stored or transmitted. Okay, it uses a nibble to represent a Denary digit. Okay, it is used in clock display, the watch which you are you have wrapped around in your hand, the clock display, or a calculator which we use in a math class, or which I am using right now. Calculator, clock display, this is where BCD is used, and the range is 0 to 9. The range is 0 to 9. Okay, decimal values. It is used in electronic devices. So there are two methods to store BCD. There are two ways to do that. So there is method 1. It could be in this way, like 0 0 0 0 0 0 1 1 0 0 0 0 0 0 0 1 0 0 0 0 0 1 1 0 0 0 0 0 0 1 0 1, which means you can store these. The way to represent these, we can represent in this way, in 4-byte way. Each byte is, there's a nibble which we store the values. This is 3, this is 1, this is 1 2 4, so this is 5. 1 2 4 2 4, this is 6, 1 2 4 5, this is 5. So this is how you can represent in this way, in this method 1. Okay, 4 single byte, representing in 4 single byte. And method 2, representing, how do we representing it? We can represent in 2 bytes. So this is method 2. You can represent in 2 bytes. So representing it, like in this way, 0 0 1 1 0 0 0 1. Let's say if I'm representing 31, then each digit will be represented in a nibble, 4-bit for 1, 4-bit for this, 4-bit, and 4-bit for this one. And instead of using 8-bit as a whole, numbers as a whole 31, we are separating it, 4-bit to represent each digit separately. So this is representing 1, this is representing 3. So as a whole, stored in 8-bit, stored in a byte. Okay, you can do in this way as well, like 0 1 1 0 0 1 0 1. Okay, 1 2 4. So this is 1 2 4. This is 5. And 1 2 4. 2 4 is 6. So yeah. So you're representing this, and you are representing this. Okay, this is how you can represent method 2 in 2 bytes, or method 1 in this way, 31 65 31 65. Okay. Okay, now let's see, there is also there is an overflow in this BCD as well. Let me tell you. So when doing the addition of any 2 decimal, give another number which is out of range in in this. If we try to do the addition of any 2 decimal numbers, okay, any 2 decimal individual numbers, let's say 5 plus 1 is 14. 14 is not in this range, we can call it overflow. The system then will flag an error, and computer needs to add this 0 1 1 0, which means 6. Okay, let's do the example. Let's suppose if I am doing the addition of let's say if I'm doing the addition of 0 1 1 1, which is 1 2 4 4 5 6 7, and doing the addition of 1. Okay, 1 to 4 and doing addition of 4. We are doing the addition. Okay, so if I do this, then 1 1 carry forward 0 1. Okay, well done. 1. Then it's going to be 8 9 10 11. It's going to be 11. 11 is not in the range in the BCD. 0 to 9 should be in the range of 0 to 9. It is 11, so the system will flag an error and will add automatically 0 1 1 0. Automatically add this. Then the answer would be, there you go. You got an extra this, and you just put 3 other zeros, and you got an 8-bit. I mean, 4-bit for individual for representing each decimal. So this is representing 1, and this is also representing 1. Same thing, 1 1. Okay, so whenever we try to add any number and it goes out of the range, we always add 0 1 1 0, because the system will flag an error and will add automatically. Or we could just do it directly, like 7 plus 4 is 11, and then trying to find what is the binary formation of this. So 1 2 4 8, so this is going to be, okay, 1 9 10 11. Okay, yeah, so this is the binary representation of this. The reason why I tried to tell you guys about that you need to add this, I just saw that in a book, in a computer science book, so I thought that it would be necessary for you guys to know that what we do, because it depends what these people are going to ask in the examination. The examiner must have thought some of they always try to give very interesting question in the exam, and we need to prepare for each and everything. Okay, so each and every detail is very necessary for you guys to give to achieve better grades, to achieve better marks. So yeah, BCD is done, and what remained now is ASCII and Unicode. So let's start with this ASCII. And what is Unicode? Okay, so ASCII is just it's a 8-bit it's a way of representing characters. You're representing characters, letters, numbers, or non-English characters and drawing characters in a 8-bit code. ASCII uses a 8-bit code to represent characters, numbers, symbols, non-English characters. And the total number of characters that are expected, that can be represented as 255 characters, can be represented. 2 of power 8 is 255. 2 of power is 250. Well, let's just forget about this. It will represent 255 characters. That's it. Okay. It's it uses the 8-bit code representing letters, numbers, and characters found on a standard keyboard. It is found on a standard keyboard. So right now you guys just learning this, that what is ASCII, because if you are planning to become a software engineering or doing computer science or doing cyber security, when you come into the university and you just start doing C language, then let's suppose if I wanted to know that what is ASCII of 56 or 78, you will get that ASCII. Let's say what is the ASCII of A. Oh, excuse me. Let's suppose you've been asked if you want to know what is the ASCII of capital A or capital Z or small a or small b, or what's the ASCII of 1 2 3 4 5, you will get that ASCII. If you are doing in software engineering, you will definitely need to understand this concept, this ASCII concept. You are using a keyboard, right? You have used a computer and you have a keyboard, a mouse. Using a keyboard, each characters represent a unique Denary number, which is ASCII. Each character is representing a binary representation. For example, let me give you an example. Let's suppose if I want to know that what is the ASCII code of, what is the ASCII character of. What is the ASCII of A? The ASCII of A would be 010000010. Okay, this is the yes, this is the ASCII code of A, of capital A. If I want to know what is the Denary equivalent, then it would be 41 in decimal equivalent. But in binary equivalent, you can just say that the ASCII of A is 41 in decimal equivalent and this in binary equivalent. Okay, so this is ASCII. It representing all the characters such as null, spacebar, hash, 01, AB or small ab. So this is ASCII code. As for a Unicode, Unicode is universal. Unicode allows characters in a code form to Unicodes allow characters in a code form to represent all languages of the world. It support 4 bytes per character. Okay, Unicode is a universal representation of characters, a universal standard that covered all languages and all writing system. It covered all languages. So Unicode is awesome. All languages. Okay, it uses 4 bytes per character, using 4 bytes to represent a single characters. So that's a lot of huge range. So this is Unicode. It's a universal representation of characters, a universal standard that covered all language and all writing systems. So this is the end of this subtopic. This is data representation. And if you guys want the PDF of this document, let me know. I will provide the link for that. The data representation is complete. Thank you so much. Take care. Goodbye.